We are here today to talk about some of the black magic, the dark art of what makes your suspension feel and ride the way that it does. Now you may think that you know how this works, but the reality is it really comes down to some very little, very insignificant looking things called shims. Now, lucky for us, we're all the way in Papenburg, Germany at the Bilstein suspension test facility. Here at their proving grounds, we've got their vehicle dynamics team, who's here specifically to explain to us how these things work. Now let's get inside and learn.
You're at Bilstein, the Bilstein test center at the Papenburg test track, in the northern part of Germany. My name is Dirk. I'm ride engineer at the Vehicle Dynamics Aftermarket division. Been there for 10 years, 20 years total in the company.
My name is Dimitris and I'm the Global Training Manager in the Bilstein Academy.
Awesome. Well, thank you both for the invite and sharing the space today. I'm excited to learn about a bunch of stuff that I honestly know very little about. So where should we realistically start?
Yeah, so we brought a prototype damper here. So I think let's take this damper, go onto the dyno, having a baseline, and then do the changes and see how those shims work.
Yeah, I can at least understand the basics there first probably, so.
Okay.
All right, let's do that.
Good.
If you're unfamiliar with what Dirk is setting our prototype damper on, it's a shock dyno. What this allows them to do is set up and adjust a damper in a lab setting prior to ever putting it on the car for a ride and handling test. A lot of times, this is used for baselining, what engineers may have spent months creating back in their R&D offices, giving precise readouts and specs to allow them to data log and compare as they fine-tune any given damper.
At the end, this curve is taken for production to control if production is according to what we had in testing here.
Okay, so that's what they'll overlay and say, like,
Yeah,
okay,
yeah,
these
yeah,
match
yeah,
up,
yeah,
this is
yeah,
what
yeah.
it should be. And then when you are looking for a number, are these fairly standard across platforms, across different lines, or is it completely different based on the ride and handling?
It's completely different. Yeah. You have heavy cars, you have light cars, you have different ratios, damper ratios in the car, and then you need different forces. So the characteristic is more or less the same, but sometimes forces are higher, lower. They are softer in the low speeds or firmer in low speeds, and yeah, that's completely different.
Yeah. Okay. Now, before we get in too deep, let's give a basic understanding and fundamentals of how a strut works and what it's comprised of in its most basic form. A monotube damper is comprised of 5 primary components. The tube is the main body of the damper, a single cylinder formed most often out of steel or aluminum that houses the other components. Then, similar to what is found inside your engine, a moving assembly. This lives inside the tube, where there's a piston that moves up and down, responding to bumps in the road. What primarily controls how the piston reacts and moves is the oil chamber. This is a section where hydraulic fluid, or oil, is stored. When the piston moves, this oil gets compressed, then absorbing the shock. Although similar to a piston in the engine, the piston within the damper is made with special valving parameters. These openings, or passages, control the flow of oil as it moves. This helps manage the impact, reaction, and movement of the strut as a whole, and in general prevents or affects the car from bouncing. The final section of the assembly is a chamber at the bottom filled with compressed nitrogen gas. This adds stability and balance to the system, because gas is needed for 2 reasons really. During compression, there's more of the piston rod coming into the tube, displacing oil, and then this is then compensated by that chamber. Second, gas pressure is required during compression. Without the pressure, there would be no motivation for the oil to flow with the damping valve. The result would be foaming inside the damper and thus no functionality.
So first we see the measurement of the friction and the gas force. And now we are going through the damper velocity, starting with 0.05 meters per second up to 1 meter per second. And basically we are using those football curves just to see if everything in the damper is working correctly.
So this is more of a QA check than anything.
Yeah, it's just if do we have enough oil in the damper? Do we have problems with the gas force? Or is anything other broken or maybe not working correctly?
All right, so we have a baseline. We kind of know at least what to compare to.
Yes.
Now open things up and start to play with some.
Now we're playing with the damper and
okay.
the shims.
Yeah. Today we're doing the bench portion of our testing on a prototype damper. Now Dirk explained that really the only difference between this and a production damper was the ability to easily and quickly unassemble and reassemble the entire damper. So the nitrogen-filled gas portion of the strut has a fill valve where he can release all the pressure. What kind of gas is?
Nitrogen. Nitrogen. We could use oxygen or just normal air, but the problem is that air has humidity, which is not so good for steel. So we're using nitrogen. Okay. Now it stays down.
And then with the removal of a seal and a snap ring, the entire piston assembly is removed and spread out on the table for us to dissect. Now, before we change any shims, let's quickly try to get a grasp on the role shims play within the entire monotube assembly. They play a crucial role in fine-tuning and damping characteristics of the shock absorber. The arrangement and thickness of shims affects the resistance to fluid flow, allowing engineers to customize the damper's performance for specific handling and ride comfort requirements. With the shims carefully lined up in their crucial order, it was time to understand the characteristics and nuances of each of them. Now buckle up, as Dirk and other ride-handling engineers have devoted their entire lives to the art of shim stacks and how that translates to your driving experience. We'll try to keep up with 20 years of understanding these things in just a few minute crash course.
That's the rebound side, and that's the compression side.
Okay, and then can you explain, I guess, a little bit? These all look a little bit differently.
Yeah.
You kind of told me a little bit earlier, but what are we looking at? These aren't just washers. Well,
that are washers.
Yeah.
Made of spring steel. You can see different sizes, different diameters. If you would touch them, or if we take a measurement tool, we see different thicknesses. And they're all used to change something in the setting. So we have those bypass discs, which allow the oil to flow through without any resistance at very low speeds. So, and those can have like a lot of those slots or just some slots. This is a quite large bypass. Don't know exactly how large it is. I would guess it's like 3.6 square millimeters.
So both the size and then how much there's opening.
Yeah, the number of the openings, the size, the thickness of the disc, and the width of each slot. That defines the overall bypass.
Right. Yeah, and in a scenario where, let's just pretend this was really open.
Yeah.
What would that do performance-wise versus if it was tiny?
So at very, very low speeds, when the body starts to move or the car starts to move, then it's quite easy for the car to move. So you will have like a more or less a floating car. But we have to keep in mind that we have a 46 millimeter piston with an 18 millimeter piston rod, which is, there's a lot of oil displaced by the piston. So that is a bit a relativation for that large bypass. So you need larger bypasses than if you only have a 32 or 36 millimeter piston. So that's...
You're moving more fluid and more...
Yeah.
Okay.
And it's all about how many oil is flowing, because we can translate that into damper velocity. That's damper velocity is nothing else than describing how many oil is displaced. And about pressure drop. And we can calculate from the pressure drop with the relevant areas that are affected by the pressure. We can calculate that into damping forces. Okay. And what we change is like the cross section of the bypass and the stiffness and the preload of the valves. So the shims are not lying flat on the piston. They have a preload, so they are like they are bended. Yeah. And with a large preload, they are bended more than with a low preload.
More fluids flowing when they're more bent.
Yes, and then we still have those shims. We can alter the number of the shims. We can alter the thickness of the shims, the sizes of the shims, the outer diameters. And some critical shims are always the cover discs, that are the large ones that are exactly the same size as the bypass disc, because they cover the bypasses. They decide about the initial opening of the whole valve. So if we do that a little bit thicker, or 2 or 3 shims of them, we would have a stiffer opening of the initial opening of the valve. So when we leave the bypass, that soft rise in damping forces going into the pressure limitation area, this gets a little bit easier when we take thinner shims. But then we lose a little bit of steering. So the overall feeling might be better, but we lose a little bit of steering.
It's almost like it affects the blend of the curve. Of like
yeah, it's how the curve goes from that rise in the bypass area into the pressure limitation area, that digressive point. And another one that's very important is that small one here. We call that the support disc. That's the last shim in the stack before the brake. And the whole package is bending around that shim. So little changes
like the
in
fulcrum point at the top.
Yes,
where it's,
yeah,
okay.
exactly, fulcrum. Yeah, that's the word I was missing. But exactly that, and we do this is always 0.5 millimeter thick, and we alter the diameter, and just in 0.52 millimeter steps, and sometimes. Once with one size, it's driving is still okay, and you change that by 0.25 millimeters and say, not good anymore.
Because it just changes everything beneath.
It changes anything beneath, below that, yeah.
Okay.
Yeah.
And then, I guess one last kind of crazy looking one is the Ninja Star top, and then the piston itself.
That works together with that shim that's still in the piston here, and that is a check valve.
Okay.
And that's on the compression side, so that's a flat-shaped spring, and that just keeps that shim in position. And if there's oil coming from there, it can open. If the oil coming from here, it's closed.
Okay.
And that leads to an effect that we call a bypass separation, because normally you can imagine with those slots in the valve, the oil can come from the inside to the outside, but also from the outside to the inside.
Right.
So if we don't use this check valve and we have bypass shims on both sides,
It won't close and
they will never be closed.
Yeah.
So both bypasses add up. In this case, maybe to 7.
Sure, they actually stack with each other, even though they're on the other side of.
Yeah, one is on the rebound side and one on the compression side.
Okay.
So they would end up and having a very, very large bypass in rebound and in compression. And with that check valve, we can close the compression bypass in the rebound stage. So in rebound, it's only one shim working.
Right.
In compression, it's both shims working.
Okay.
So and that's always what you want in, I would say, 99% of the cars. You want a steeper rise in rebound than in compression, or higher, in total higher rebound forces than compression forces.
Okay.
There are some cars, some super sport cars. I know the Audi R8, I think that had it flipped around. That had a more compression than rebound, but that's
Rare.
really not the standard.
Yeah, that's not a normal car either.
Yeah.
Okay, so from here, if we want to see some extremes, so like, could we do a stack where maybe we don't put the check valve in, or maybe like where would you reorder these, or if you were to make a mistake, where would a mistake happen, just so we can see like an extreme case?
The mistake is I would do a wrong preload disc
Okay.
to change the preload significantly. Higher or lower, I have to see, and maybe do a wrong bypass disc. So we should see a completely different first gradient of the curve, and the total forces should be completely different, at least in one direction.
Okay.
So what we always do is when we take shims, we measure what we have. That's a 28 by 0.3. So we take that out and we put in a 28 by 0.2. So that's 1/10 of a millimeter more preload, or when we're starting with 0.2 millimeters, now we have 0.3 millimeter, 50% more preload should end up in 50% more damping forces. So that's really a big change. Normal changes, you talk about like 10% or something.
Oh wow, okay.
Yeah.
That's extreme.
And then we have that bypass shim with a large number of slots, so that's a very big one, 0.15. Size is 36.5. That's normal. And now I'll take one with only 2 slots. So I think that's
restricting
0.9 millimeters, and that's 3.6 millimeters square millimeters area or cross section. So we will take those in, and we should see a significant change in damping forces on the rebound side.
Okay.
Because that's a change only on the rebound. So just everything goes on that.
It's kind of cool because we saw this happening in Ennepetal yesterday at the factory.
Yeah, that's what the ladies do in the...
Yeah.
For context, the previous day we had been visiting one of Bilstein's production plants, and there was an entire room filled with shims and employees shimming dampers, based on specifications made here by the ride and handling team at Papenburg.
So I'll do it one by one. Some other might stack them up or pile them up. And okay, now we have the check valve, and then what we have to check always is that, so now we have an oily part, that this shim still is in position. If that is out of position, then we would have some trouble. You can see that should work. So now we have the preload, the changed preload, and the different bypass. Okay.
All right, so we have a full assembly now.
Yeah.
Back to
That's-
real reassembly.
Yes.
Okay.
Now we're going back to make a shock of it.
With the new shim stacks reinstalled with the piston assembly, it was time to quickly and conveniently rebuild our strut, filling it with fresh oil and gas accordingly.
That's our gas filling machine. We have a computer here that controls the gas pressure, and this is just a fixture to open and close that valve with the gas flowing around it. So it's just getting in here. We open the valve. I'll address the 18 bars that we want to fill. Start. So piston rod is coming out now, and we did a very low, small bypass and rebound. You see that? So the piston rod is coming out really slow.
Yeah. Even with all that pressure.
Yeah. Okay, so now it's fully out. We're waiting until the display gets green. That would tell us everything is okay. So there we are.
Once it was back together, we were ready to go see what the outcome of our mistakes had been. For that, we headed back to the shock dyno that we had baselined on earlier in the day. So that's what you can't do at home.
That's it. That you can't do at
You
home.
can't do that at home.
You can drill a hole there to get the gas out, but you will
You
never
can't
get
get
it
it
back in again. Okay, so it's back in the dyno, and I'll start the measurement. So first strokes are for getting the rest of the air that's still in the oil chamber out of the damper. And then we start with the gas force and friction measurement, and okay, what we can see here, that is, the drop here is much higher than it was in the first measurement. So I guess also from what I heard already from the dyno,
Something's different.
something's different, and I think we have more forces in the damper. Yeah, but at least the friction looks very good now with that other scale. So yeah, that's really different.
Yeah, because even this was more round.
Yeah, this was more round. So you see that we almost don't have a bypass now because it's already the shim stack that's opening.
And does that look more extreme here because that was a low speed measurement? So
Yeah, the forces are higher, and when I change now from that football curve to the force velocity curve, and I integrate our first measurement, we only see that little bit of bypass there. That's because we have that 46-18 damper. Yeah. So we close the bleed, so also the first speed goes up in forces, and we raise the preload, so that whole part of the characteristic was moved up parallel to higher forces. And we only see that, as I told you when we looked at the stack, in compression both bypass shims are working together. In rebound it's just the shim working that we changed. So in rebound we have a big change, and in compression we have the change from, I think it was it still uses the other big bleed. So we had like 7.2 square millimeters
so it's almost
before,
averaging it.
and now it's 4.5 in the middle. And when we would look at the forces, we see that this is almost half the forces.
Makes sense.
So the change just in rebound. So again, not a change that anybody would drive in the car, because the right feeling would be like the car would be very edgy on the steering, will react very instantly, and with those high forces and more preload, the car will feel like it always tugs you down. When there's excitation in the car.
It's just because there's so much pressure.
Yeah, so much rebound pressure.
Yeah.
So much
Like the
rebound
tire's trying to
forces.
stay on.
The car tries to stay on the road. If the car goes down, it takes the seat down, but you as a passenger, you first stay up and then it tucks you always down. That's not a driving behavior that you want to have.
Now, in a scenario that you wanted that darty feel, something very
Some
reactive.
cars might need that. So
how would you balance that so that it wasn't porpoising then, or if it wasn't?
So in fact, that's for that system, the bypass is way too small.
Yeah.
So you would never use a bypass like this.
Sure.
We would be going down from, if we had 3.6, we might go down to 2.4 or 3. And then there's already enough change. And if we need higher forces, and we already have a lot of shims in the shim stack, then I would go down with the thickness of shims now. So taking a shim out maybe, if I want to stay with the higher bypass. But in fact, we did, the preload step was 2 steps. So maybe I would end up to do just 1 step. So now we raised the preload by 0.1 millimeters, and then I go down to 0.05 millimeters. Yeah.
You're talking about the handling of the vehicle, the way it feels. Obviously that can differ from person to person. So when you guys are trying to find that ideal setup or the optimal setup, what does that look like? Is it, you driving the car 10 times in a day? Is it switching out drivers, or what's the setup?
I could tell that's the best of our job.
Yeah.
We know our customers and we know what our customers want, but we don't have them in our car. So they can't tell us, I want that, that is good or that is not good. When we do a mass production, our OE parts, then there's always the customer with us in the car, and he says where he wants the car to be. So what we do, we are in total 5 people in the aftermarket ride and handling department in Germany. And normally when we are here in Papenburg, we have 2 cars with us, working on both in parallel. So we have 2 teams and they always switch cars. So both teams drive both cars. Okay. Because we have older people in the car, we have younger people in the car then, and we talk about what we want and where we want to go. And at the end, we get a level that's suiting for everybody.
Do you almost work separately? Like, will they create a damper that they feel like one team that's ideal, and then
no, because it's just
sharing back and forth.
We're sharing.
Yeah.
It's always normally both cars are rebuilt at the same time, so both cars are ready. So both teams go out, they come back, change cars, go out and back again, and we're talking about both cars and defining the next changes for every car.
Now, is this unique to the way Bilstein is set up, both within the ride and handling department and then just obviously like the shock absorbers themselves, or is this kind of industry standard?
I don't know if it's industry standard. I think it's more than industry standard, because I know that other aftermarket producers, they also have a ride and handling standard, because everybody needs to check if their parts are fitting in the car, because we don't have a car when we start the design of the dampers. We only have maybe the series parts to take measures from, but we never see if we can install them easily in the car. Okay. But I think what we do with regards to how the car drives afterwards maybe is a bit more than others do in the aftermarket industry. Yeah. Normally now, if that was a change that we wanted to do and we are lucky with the results, then the shocks would go back on the car, tires fitted, car on the street, and we go out for a ride.
Yeah, all right.
Let's do.
Let's do that.
Now, we didn't have the car that this prototype damper belonged in, but we were lucky enough to get shown the ropes around the facility from Dirk in our Passat wagon. All while following Bilstein's super project that was sporting a new set of Bilstein Evo T1 dampers designed for the T90 chassis.
All right, so Dirk, we're just in the Passat now, but you're gonna give us a little bit of a tour?
Yeah, I will give you a tour around the proving grounds here. It's the ATP Papenburg proving ground that was once built by Mercedes-Benz, or the Daimler Corporation, back in, I think it was 1998. They use it as a proving ground, then they sold it, and now it's open to everybody. It has around 80 hectares. I don't know how many acres that is. Of fenced area, and around 70 kilometers streets, so different from the oval course, which is more or less an autobahn, to rural roads,
There's a little bit of everything.
gravel
Here, right?
handling track, wet handling track, braking tracks, vehicle dynamics area. So I think there's nothing that you couldn't do here. So this is a oval course. The length is about 13 kilometers. 2 bank curves with 49 degrees banking, so you can go at 250 kilometers per hour without having the hands on the steering wheel. And on the inside there are several modules. This is called Bilstein. This is a rebuild of a short part of a autobahn in the near of Sindelfingen, where Daimler has its R&D center. This part will be a rebuild of the American freeway hub. That's the rebuild of a highway somewhere between or near San Diego or Los Angeles.
Wow. So is it a lot of potholes?
No, it's just the concrete washed out and with the steps up and down between the single concrete plates. So yeah, so we're just going the first corner. And of course I will go to the top of the next curve, on the top of the banking with you. Now it starts. Yeah.
That's cool because you can barely see it.
So this is a behavior that we absolutely do not want to see on our car. So car uses the whole travel, especially on the rear.
Yep.
You feel it going into the bump, stop and pushed out again.
Yep, sure do.
Sorry for that.
No, that's good.
Sorry, not sorry.
Cameraman's worst screen.
Yeah.
So this is intentional.
Yeah, this is intentional. So that's the strange thing about proving grounds. The road is intentionally built bad, in a really bad condition. So normally you would aim for a very smooth ride, not here, no.
This does feel like home though. I feel like I'm back in America.
And this car actually feels quite good on this.
Yeah.
So when I guess when we take the Supra, as it is a very sporty car, you will feel a lot more short displacements, and it will be more uncomfortable than this one. Now there's another track. We don't use that very often, but this does the same as the other one, but sideways. So rolling, but that's really good. That's really good what the car does here.
Yeah, this feels pretty compliant.
Yeah, it will get worse now. So still a lot of travel, and yeah, but that's typically for a stock suspension for a comfortable car.
Yeah, not a race setup.
Yeah.
You can see how amazing the versatility of such a facility allows the Bilstein ride and handling team to throw absolutely everything at testing a car. From racetrack conditions, back roads, to a section of the oval that they even call the American Highway, and basically everything in between. And we can't help but talk about our favorite feature, the absolutely insane 45-degree banked wall. Dirk and Demetrius were kind enough to give us a look at what a normal day of testing and tuning would look like after hitting the proving grounds, and then needing to make changes accordingly. It was interesting to hear the nuances and small tweaks they would make, both from the on-track data and drive characteristics felt in their hands. They'd then output that onto the computer in order to hand it off to their team.
So from my impression, the car was a little bit too loose, so initial roll was a little bit too weak, and I want to get that car closer to the steering. So a little bit more rebound, first shim. So then we would just create the new setting. We need a new number. And then we will make the first cover disc also in 0.35.
Yeah.
And we're closing down the bypass a bit on rebound from 2.4 to 1.8. And then that's it. So hopefully we get that initial feeling a little bit better. Yeah? But we see the changes, and that's what the mechanics see or get as a printout, so they directly see which shims they need to change. And that's basically it, what we're doing with this. And we have the comparison in the forces and the shims, and yeah, so we can see what we did over the week and how the setting developed.
No, but really, this was great.
Like,
It was really fun.
I would rather go through like a 10-week training course and try to understand, you know, how to actually do the work and
make
do
it
all,
a year.
Yeah, but
Make it a year.
Yeah. 4 hours, 10 days, 10 weeks, 10 years probably, right?
Okay.
But no, thank you guys for everything. Really,
you.
it was
You're
great,
welcome.
and
You're welcome.
learned a
Thank you
ton.
very
Hopefully, we
much.
taught people a lot too,
Yeah.
which is cool. All right, well, hopefully you guys learned as much as I did today. What an amazing opportunity. The whole landscape of this place in Papenburg, the Bilstein team teaching us all this. I learned a lot. Hopefully you learned something. Obviously this is super technical. I'm still a little confused, but I definitely know more than what I walked in with. Probably leave the shimming to the experts, but hopefully you can enjoy your car a little bit more now, knowing all the nuance and all those little bits and pieces that the engineers and the testing teams actually do to make them feel the way that they do. We'll see you on the next one, and thanks for watching.